So for those of you that don't know me, my name is Broderick, and I'm here today to give you a bit of a rundown and hopefully understanding about what my proposed research is going to be. So I'm going to be investigating the dosimetric impact of the mechanical movements of the Linac gantry during treatments with small fields. So a bit of a mouthful, and hopefully at the end of this presentation it doesn't seem that big of a thing. I'd also like to thank in advance my supervisors Pejman and Tom, who will be guiding me through this project. So before I really dive into my project in a lot of depth, I wanted to give a quick background about the area that I'll be working in. So one of the things of note in the past few years as modern radiotherapy has been developing is increasingly we've been using smaller and smaller fields in treatment techniques. And so that's aspects involves things such as volumetric modulated arc therapy and also stereotactic radiotherapy. And you may ask what exactly is a small field, and I myself had that question as well. And unfortunately, the definition isn't super defined. It's varied over the years, and different groups around the world have different definitions. However, a general guidance to sort of give you an understanding about what fields we're talking about here is that they're generally under a size of 3 centimetres by 3 centimetres in dimensions. And the benefit of small fields and why these have actually become more and more frequently used are a number of aspects, but the first one is that as our detection methods have gotten better and better, we're detecting tumours earlier in patients, and that means that we have smaller treatment volumes that we want to treat. So small fields obviously help us deal with those. However, they also are quite useful for larger tumours as well, because tumours aren't homogeneous across the entire mass of themselves. And so what they've found is that there are clinical benefits of applying small fields and treating different areas of the tumour with different doses of radiation. And as I'm sure you're all aware, medical Linac accelerators, or the Linacs, are the most commonly used machine for external radiotherapy, and I predict that they will be for quite a long time, given how frequently and how common they are across the globe. There are obviously other tools out there and other machines that can deliver small field treatments, so you've got things such as CyberKnife and those sorts of machines. However, the Linac is the most widely used machine out there. So one of the things about the Linac machines which is important to note is that they have potential mechanical errors which can affect how the treatments and how the doses they deliver come out. So one of these mechanical errors of note is Gantry sag, and here is just a little picture from a paper which has been conducted into quantifying what the Gantry sag changes are. This is just different millimetre shifts at different positions around the Gantry's motion. And this Gantry sag is caused by the massive amount of material and heavy tons that are stacked into the Linac gantry head. So you've got things in there such as your shielding, you've got all sorts of different generation and shaping systems, and basically a lot of really heavy stuff. And naturally, heavy stuff is affected by gravity. And this gravity effect on the Linac gantry as it goes around the machine is that you get a bit of a wobbling effect. So you don't have this ideal circular path around the whole motion, you get a bit of a wobble as it goes around. And as a result of that wobble, you get a change in the isocenter's position ever so slightly. So it moves as the gantry moves around different angles. And it should be noted, of course, that this isn't the sole mechanical imperfection that Linacs can have. There are other areas that can cause issues with the Linac, and such as misalignment of components or just general aging of the machine. So, for example, the ball bearings used in that motion can wear down over time, and that can slightly modify how it performs. And previous papers have proven that there is, there's instant connection. Previous papers have proven that there is a correlation between the age of a machine and its performance, as you would generally expect. However, that being said, the gantry sag is one of the more well quantified aspects of the mechanical error, and aspects such as just misalignment of components or random pieces of machinery failure aren't as well quantified. And so for my project, I'll be focusing on the gantry sag's effect as an indicator overall of the mechanical imperfections that you can get in a Linac. Another thing to note is that we have these small isocenter changes, and as I'm sure you're all aware, quality assurance as a broad category is a very important component of a medical physicist's job. Obviously, if we fail in quality assurance, there's going to be a lot of problems with our treatment and our doses that we deliver. Now, the TG142 is one of the most common reference papers on this area, and they recommend that you have an isocenter variance of no more than 1 millimetre in annual quality assurance. However, there are a few things to note about this guidance. First off, it's published in 2009, which It doesn't seem that long ago, but as I've come to understand, in the world of medical physics, is actually quite a long time ago. Also, this is before the use of single isocenter radiosurgery, so it's something that hasn't really accounted for those changes that we've had in recent years. And also, as I sort of mentioned at the start, small field radiotherapy is becoming more and more frequent, and also we're using smaller and smaller fields. So although I sort of had that guidance of 3 centimetres by 3 centimetre as a guidance of what a small field is, there have been recent studies also that have been looking at using very small fields, which are even smaller, for different treatment modalities. So this sort of comes into where my project wants to sort of explore. So the aim of my project is really to evaluate if that current tolerance level that is quite widely accepted is acceptable for small field treatments such as stereotactic radiotherapy and those sorts of aspects. As a sort of sub-aim around that is I aim to computationally evaluate the dosimetric effect of that isocenter uncertainty caused by that mechanical motion that I outlined and how that will change things. And to do that, I aim to basically compare the dosimetry for 2 different plans. So one for where we account for that mechanical motion and one for where we don't account for it. So why is this actually significant? As I mentioned, quality assurance is very important. And this project hopes to sort of help in the field of understanding our use of quality assurance for small field treatments. We hope to provide a bit more data to back up what we're actually doing in quality assurance, because obviously having data and having informed decisions about what we're doing is very important. And also this is pioneering research in the field. This is something that hasn't really been explored in a lot of depth previously. Now, there are, however, some relevant prior studies, and I apologise, this slide is a little busy, but the key thing to really note here is, and I'm not going to try and use the laser pointer, but we have these little patterns which have been developed on understanding how the isocenter will move as the gantry angle changes in a linear accelerator. And this has been conducted here at Sir Charles Gardner and with the UWA research group. And we've basically developed these patterns which basically map where a different angle is and what the isocenter movement will be for each of those angles. And that has been conducted for all sorts of different machines by Pejman and various other co-researchers. So we have really good data sets on the variant set, the Electa set, and the Siemens machines. And the way they did this in very, very brief terms is they measured the gantry sag using an EPID method, where they would basically take a series of images as the gantry was rotated around, and they would track how the positioning and the shadows of ball bearings changed in that motion. Also of note is work done by Tom, who's also going to be one of my supervisors, and he's investigated this effect for VMAT generally, not specifically some small fields, however just generally for VMAT. And one of the results from his study is that he found that 1 millimetre was, he had data to support, is an acceptable metric for us to use in quality assurance. And here's just one of the graphs where you can see the change in the isocenter shift and the D98, or the dose given to 98% across the different machines for the prostate, which is one of the treatments that he looked at. However, there are a few areas that I hope to improve on and hope to sort of build upon from his study. So the first one is that he used the Electa Monaco treatment planning system, which is great. However, it does mean that there is limited ability to actually modify that system. It's a commercial software, and as the world actually is, very generally, they keep things locked down, so they don't let you just play around with that equipment. And as a result, he was forced to discretize his plans and actually modify the DICOM file, which I'll explain in a second, that was feeding into the treatment planning system, as opposed to directly modifying how the system is accounting for these angles. So he also at the end of his paper suggested future research for stereotactic plans, and that's where I come in, so exploring this for those sort of small fields. So a bit of context for those of you that haven't delved into the depths of treatment planning systems, and perhaps you may not be very interested in it, but the DICOM file format stands for the Digital and Imaging Communications in Medicine format, and it's an international standard to basically help us pass information between different medical machines. Obviously, if every single manufacturer used their own format, there'd be a lot of difficulties in passing information between things. And it sort of uses object-oriented programming principles where you basically store data in just different data elements. Specifically in my project, I'll really be utilising DICOM RT files, which stands for radiotherapy files. And these are sort of an expansion on just a standard DICOM file in that they also hold information regarding the plans that you want to do, and also the CT information, so you can easier visualize what's going to be happening. And as I sort of mentioned there, they hold all the information which you could possibly need when you're undergoing radiotherapy treatment. So you've got your geometric data, your dosimetric data, you've got your beam angles, your collimator angles, basically everything you basically need. Now, treatment planning systems, which you're actually feeding these DICOM files into, they're really the core of modern radiotherapy. So these enable us really to do a lot of the things we weren't able to do way back in the day. So they basically will determine the plan of what we're applying in our radiotherapy treatment, things such as inverse treatment planning. They allow us to calculate expected doses and really optimize how we apply our radiation and what dose we apply to a patient. But as I mentioned, commercial software is closed source. So that leads us into MATRAD. So MATRAD is an open source software which enables us to conduct treatment planning, simulations and treatment planning calculations. So it's based in MATLAB, and it was developed by the German Cancer Research Center. And that sort of leads me into what I'm actually planning on going and doing in my project. So the first step is really going to be understanding what these DICOM files are and understanding what the actual code behind this treatment planning system is. Because to do any implementations or any changes on it, I need to obviously understand down to the code level of what is happening. But this is also going to be a bit of a learning process for myself. I haven't delved into treatment planning before previously, so I'm hopefully going to develop a really good understanding of treatment planning and also get to improve my coding skills in a real-world context or in a real-world application scenario. So once we have the sort of understanding about what the code that I'm going to be working on is, I actually need to make these modifications. And the first modification is to actually let it handle different isocenters. So currently treatment planning systems, and this is why Tom wasn't able to submit his plan with different isocenters, they don't support you having a different isocenter for every beam or every position of your beam. They basically go, oh, isocenter is the same, why are you trying to tell me different things? Error, throw back and stop. So that will be the first sort of step in this code modification. And I'm going to need to modify the actual raw source code of this treatment planning software. So I need to make a forked version of it. Once I've modified it to handle the different isocenters, I then need to actually input this real-world data we've gathered at the hospital on the different angles and the different positions of the gantry and how that affects the isocenter. So at the end of this, I'll hopefully have a program which can take in this data and it can spit out either a normal plan where it just doesn't factor in the isocenters or one where it factors in the isocenter variations. So on the third step, I need to actually collect this data and actually get some treatment plans through the software. So I'll be using treatment plans from Sir Charles Gairdner Hospital, and specifically I'll be focusing on those with use of small fields. So that will be things such as VMAT, stereotactic ones, and any other potential ones. These small field treatments aren't solely limited to these types of modalities, so any other plans obviously very good to get a bit of perspective and a better understanding of how the effects are happening more generally. So once I've got these plans, the next step is going to be actually evaluating them. Now, here are a few different metrics that I plan on using, but obviously this isn't an exhaustive list of every single possible metric out there. And I'm sure that over the course of my project, I'm going to discover a lot of other metrics and a lot of other ways that we can quantify how these plans have varied. But so a few ones to sort of start with are sort of percentage tumour coverage, obviously very important for treatment outcomes, organs at risk percentage covered, again, also important, and gamma index analysis, which I included a very brief description of how it works here for those of you that don't know, but in very, very layman's terms, you basically have two plans and you look at the voxels, which is a sort of expanded version of a pixel, for those of you that haven't delved into this area too much. So you have the voxel in this plan, and then you have the other plan. And then you look at how, for a small neighborhood, this voxel compares to those in the other plan. And if you find there's a match, so this voxel matches this voxel and it's only like 1 millimeter away, then you go, great, there is an agreement. And so you do that for every single voxel in your original image that you're comparing against. So once you've gone through this whole image, you'll get a success rate or a general guidance about how similar these plans are. And also this guidance from TG119 generally suggests that a 90% pass rate with a 3 millimeter neighborhood in the other plan is a good acceptance guidance that you have got plans which are similar. So that overall brings together my full research plan. On the way, of course, I'm sure there'll be many challenges and many things which will pop up as I'm exploring all of this, but this is the original plan for now. And here are some references just covering everything from today's slides. Thank you for listening, everyone.
Great. Good timing. Exactly. Any questions from Broderick? Great. Yeah.
So one of the things that we do, Sheet can correct me if I'm wrong, is a patient-specific QA process where we reproduce the plan on a phantom and then deliver that treatment. It would be really nice to know how sensitive that is to its ability to pick up this sorts of mechanical issues. And it might also be interesting to go back through the records to see if there's any correlation between what that process has found and aspects of the plan, like how small the volumes were, etc. Maybe you've already done that process, I'm not sure.
We can have a look. List everything.
Yeah, and I definitely think,
That would be possible?
yeah, I think, like once the software is set up, we have the code which will be able to implement this. And so we'll be able to put in any sort of other sort of branches of exploration and put in other bits of data and even more historical data and sort of see how that affects things. So yeah, for sure.
From Zoom, Monia, do you have any questions?
Still there?
Yeah, all of us by my side. Thanks.
Cool. Great. Yes.
Everyone, you were just using the MATLAB program in MATLAB. Is there a Python alternative you considered?
Unfortunately not. So one of the things about MATLAB is its ability to handle sort of matrices and do those sort of mathematician processes. So it's sort of well optimized, or this sort of operation is well optimized to happen in MATLAB. So yeah, Python isn't really as optimized as software for that type of thing that will happen. So unfortunately, no, there's not a Python version of this.
Yeah, I have some questions. Did you mention like the sizes of fields that you're going to use, or do you know like what kind of range you're going to use?
So the general size of the fields will just depend on really what the hospital has available for me. I'll probably, be constraining things to have that sort of generally under that 3x3 small size. Otherwise, we're not really looking at small fields.
Yeah.
And also because Tom has done that work previously with larger fields, there's no point sort of rehashing and looking at those bigger ones. So, if there's time, and I've got lots of free time and I want to sort of explore, I could sort of re-look over Tom's work and sort of see if I get any differences when I'm accounting for it in my treatment planning system versus in the actual method he used, which was modifying those DICOM files. Yeah, it really will depend on just what is available and what the hospital can pass me. Yeah.
So it looks like a massive project. So like the coding side alone is huge. But I'm just wondering, have you looked into any problems with like small field dosimetry at all?
So yeah, there is definitely, small field dosimetry is an area that is challenging and is definitely being explored in other areas. But in this case, I will probably not necessarily have a lot of time to dive into that. But yeah, I'll just be looking at how the dose from the treatment planning system comes out, as opposed to measuring the dose in the real world. Yeah.
Yeah, there's a lot to do, like just understanding the code alone.
Yeah.
Yeah.
Even you can consider dialog files and MLC movements.
Yeah.
So that's another extension.
Yeah. So lots of, I think once I understand the code, there's definitely, once you can understand a treatment planning system, you can do all sorts of fun stuff and exploration. So yeah.
Great.
Cool. Thank you.
Thanks, everyone. Brilliant.